Mind your decisions, I'm Presh Talwalkar. The following problem appeared on the 2002 to 2003 British Mathematical Olympiad. The challenge is to write a complete proof. It is not sufficient to provide a numerical answer alone. Find all solutions in positive integers a, b, and c to the equation a factorial multiplied by b factorial is equal to a factorial plus b factorial plus c factorial. I thank Nahian for the suggestion. Pause the video if you'd like to give this problem a try, and when you're ready, keep watching to learn how to solve this problem. We will get started by noticing a symmetry in this equation. What would happen if we transpose the variables a and b? Because multiplication and addition are commutative, we have an equivalent equation. Therefore, if ABC is a solution, then we know BAC is also a solution. What this means is that if a solution exists, then a solution, ABC, with A less than or equal to B also exists. Without any loss of generality, we can suppose A is less than or equal to B. The proof will proceed in the following 4 steps. First, we'll prove that 3 is less than or equal to A. Then we'll show that B is less than C. Then we'll prove A is equal to B. And finally, we'll prove C is less than or equal to A plus 2 and solve for the numerical answer. Let's get started by working out a few cases. Suppose A is either 0 or 1. Then A factorial is equal to 1. We substitute that into the original equation and then simplify. This equation only has a solution if 0 is equal to 1 plus c factorial. But no solution exists for this equation where c is a positive integer. Therefore, a cannot be equal to 0 or 1. We then consider the case a is equal to 2. This means a factorial is also equal to 2. We substitute that in, and then we simplify the equation. Notice there is no factorial that's 2 more than another factorial because the factorial sequence goes in order 1, 2, 6, and so on. Therefore, this equation also has no solutions for integers b and c. Therefore, a cannot be equal to 2. This means a has to at least be equal to 3. Then we've supposed that a is less than or equal to b, so we can add that onto the inequality. From here, we're going to prove that b is less than c. To do that, we'll assume the opposite, b is greater than or equal to c, and then derive a contradiction. We can bound the sum a factorial plus b factorial plus c factorial as follows. We've assumed that a is less than or equal to b, therefore a factorial will be less than or equal to b factorial. Then b factorial is equal to b factorial. We can then bound c factorial because we've supposed that c is less than or equal to b. Therefore, c factorial will be less than or equal to b factorial. This sum will be equal to 3 multiplied by b factorial. So we have an upper bound on the sum. But we can also derive a lower bound. This sum is equal to a factorial multiplied by b factorial. We know that a is at least equal to 3, which means this is at least equal to 3 factorial multiplied by b factorial, which is equal to 6 multiplied by b factorial. Therefore, we've shown the upper bound of the sum is actually lower than the lower bound, and that's a contradiction. Therefore, our assumption that b was greater than or equal to c must have been wrong, and we've shown that b is less than c. Before we proceed to the next part of the proof, I'm going to go over a bit of notation. This notation means that m divides n. It's equivalent to saying n is divisible by m. It's equivalent to saying n is a multiple of m. And it's equivalent to saying that m is a factor or divisor of n. 2 divides 4, 3 divides 12, but 2 does not divide 5. Now let's show that a is equal to b. To do that, we'll assume the opposite, that a is not equal to b. This means 3 is less than or equal to a, which is less than b, which is less than c. So we go to our original equation and we'll divide both sides by a factorial. This simplifies to be the following equation. Notice the left-hand side is b factorial, and the right-hand side will be the sum of three integers. This is because b and c are greater than a. So b factorial over a factorial is an integer, and c factorial over a factorial is an integer. Now, since b is at least equal to 3, we know that b factorial is an even number. That's because every factorial above 3 factorial will be an even number. Consequently, the entire right-hand side, which is the sum of integers, has to be an even number. Now, since 3 is less than or equal to a, is less than b, is less than c, we know that b is at least equal to a plus 1, and c is therefore at least equal to a plus 2. But then, a plus 2 multiplied by a plus 1 must be an even factor of c factorial over a factorial. That's because the product of any two consecutive numbers is an even number. Consequently, 2 divides c factorial over a factorial. Now, in order that the entire right-hand side be an even number, we must have 1 plus b factorial over a factorial is an even number. But 1 is an odd number, which means we must have an odd number plus an odd number. So b factorial over a factorial must be an odd number. Now, since b is greater than a, this implies that b is equal to a plus 1. The reason is that if b was at least equal to a plus 2, then it would have an even factor of a plus 2 multiplied by a plus 1, which is not possible since b factorial over a factorial is an odd number. So from here, let's consider what happens if b is equal to a plus 1. We'll substitute that into our equation and we'll simplify. We now consider the divisibility of this equation by the factor a plus 1. The left-hand side is a plus 1 factorial. Naturally, it has a factor of a plus 1. The right-hand side will be the sum of three integers. Naturally, a plus 1 has a factor of a plus 1. Now, c factorial over a factorial will also have a factor of a plus 1 because c is at least equal to a plus 2. Therefore, for the right-hand side to be divisible by a plus 1, we must have a plus 1 divide 1. But that means that a is equal to 0, and that's a contradiction because we know that a is at least equal to 3. Therefore, our original assumption was wrong. We cannot have a is not equal to b. We must have a is equal to b. We will then consider the next step. From here, we want to prove that c is less than or equal to a plus 2. We'll again take our original equation, divide both sides by a factorial. We're going to substitute that a is equal to b, and then we'll simplify this equation. We'll simplify it a little more, and then we'll subtract 2 from both sides. We'll again look at divisibility. Since 3 is less than or equal to a, we know that a factorial is divisible by 3. However, we then know that a factorial minus 2 is not divisible by 3. This is because a factorial is a multiple of 3, and we're subtracting 2 from it. Therefore, 3 does not divide a factorial minus 2, which means 3 cannot divide c factorial over a factorial. Now, if c was greater than or equal to a plus 3, then c factorial over a factorial would have a factor of a plus 3 multiplied by a plus 2 multiplied by a plus 1. But 3 would divide this product because one of 3 consecutive numbers must be a multiple of 3. Therefore, we must instead have c being less than or equal to a plus 2. So we only have 2 possibilities to consider. Either c is equal to a plus 2 or c is equal to a plus 1. Let's consider each one in turn. Suppose c was equal to a plus 2. We'll substitute that into the equation. We'll then simplify this, and now we'll do a little bit of algebra. We'll multiply on the right-hand side, and then we'll take all of the a terms to the left and put all of the constant terms on the right. Now in this equation, notice that every single term on the left-hand side of the equation is divisible by a. This means that 4 has to be divisible by a. But since a is greater than or equal to 3, the only way this is possible is if a is equal to 4. So let's substitute a is equal to 4, b is equal to a, which is equal to 4, and then c is equal to a plus 2. So c is equal to 6. Well, if we substitute that into the original equation, we actually get something that does not work. 4 factorial multiplied by 4 factorial is not equal to 4 factorial plus 4 factorial plus 6 factorial. Therefore, c is equal to a plus 2 does not lead to a solution. So we instead need to consider the other case, that c is equal to a plus 1. Now, in this case, we'll substitute in, and then we'll simplify. We'll move the a terms on the left and the constant terms on the right. Now, from this equation, a does divide a factorial minus a, which means that a would have to divide 3. Since a is greater than or equal to 3, this means that a is equal to 3. So we now consider the possibility that a is equal to 3, b is equal to 3, and c is equal to a plus 1, which equals 4. We substitute that in to the original equation, and ta-da! We found the unique solution. This is an incredible problem, and the proof is just so wonderful. Thanks for making Mind Your Decisions one of the best channels on YouTube. As always, thanks for watching, and thanks for your support.
Warning.